Assalamu alaikum and very good afternoon to all. I am Abu Rafi Muhammad Jamil. I am going to present my paper titled An Experimental Analysis of Reward Functions for Adaptive Traffic Signal Control System. First of all, I would like to discuss briefly about Intelligent Transportation System, which is an integrated system designed to improve the road safety, efficiency and comfort. It combines information technology and telecommunications and provides real-time information for road users and transportation system operators to make better decisions. Adaptive Traffic Signal Control System is a subsystem of Intelligent Transportation System. It aims to improve the performance of traffic light control system, takes the real-time traffic information as input and adjusts the traffic light duration dynamically. Recent literature used reinforcement learning for adaptive traffic signal control system. Therefore, I would like to discuss briefly about reinforcement learning. In reinforcement learning, the learning agent interacts with the environment. The agent observes the environment and takes action to the environment. According to the action, the environment changes and a scalar reward value is gained from the environment. The reward value is the feedback from the environment for the taken action. According to the reward value, the agent understands the effectiveness of the taken action. If the reward value is high, then the taken action is considered as a good one, and if the reward value is low, then the taken action is considered as a bad one. The action is judged according to the reward value. Therefore, if the reward value is not calculated properly, it can gives the agent wrong feedback about the actions. So, designing the reward function is one of the main issue in reinforcement learning. In traditional reinforcement learning, the agent saves the experiences, which is the state, action, reward and the next state, in a tabular fashion. In deep reinforcement learning, instead of a table, it uses a deep neural network as a function approximator to maintain the exponentially increasing combination of states and actions. The reward function can be categorized into two: the single objective reward function and multi-objective reward function. In single objective reward function, one single parameter is used to design the reward function. On the other hand, multiple parameters are used to design the multi-objective reward function. The multi-objective reward function is expected to perform well than the single objective reward function, as it optimizes multiple parameters at a single time. The above discussion derives us to our objective. The objective of this paper is to make a comparative study and experimental justification for choosing the appropriate reward function for different traffic scenarios. The overall learning process is described in this picture. The experience is saved in the experience replay memory. A random sample is gained from the experience replay memory and it is sent mini batch by mini batch to train in the network. There is two different neural network, the deep Q network DQN and the target network. The deep Q network predicts the immediate reward value of a given state, and the target networks predict the future reward value of a given state. There is an optimizer that optimizes the loss of the DQN and the target network. The DQN is updated at every time step, but the target network is updated after a fixed amount of time. The designed simulation, the state and the action is described here. The state is designed with three different parameters: the queue length, waiting time and number of vehicles in the lanes. There are two incoming lanes for all the road in our simulation and two outgoing lanes. In the road simulation, there can be two different phases. In one phases, the vehicles heading north and south can pass the intersection, and the other phases, the vehicles heading the south and in the east and west, they can pass the intersection. As there are two different phases in the traffic simulation, the agent have two different actions, 0 and 1. 0 means we will not change our current traffic phases, and 1 means we'll change our current traffic phases to get to the next phase. We have used 6 different reward functions in our experiment. Among them, 4 are single objective and 2 are multi-objective reward functions. The 4 single objective reward function is designed considering the difference of cumulative delay, the difference of waiting time, the difference of queue length, and the difference of travel time. The 2 multi-objective reward functions are designed considering 5 parameters and 6 parameters. Both of them we have used in literature, which is mentioned in the footnote, and we have give the reference. Here are the system parameters. We have minimum time interval of action is 5 seconds. That means within 5 seconds the traffic phase will not change. The learning rate for the agent is 0.005. We have a memory size of 1000. That means we can have 1000 samples in our experience replay memory. The sample size is 300. That means at a time we take 300 random samples from the memory and send it to the network for training. We have a minibase size of 200. That means the network takes 5 samples at a time for the training. We have the training epochs of 500. Update period of target network is 5 seconds. The gamma value, the epsilon value for exploration is 0.05, and we have discount factor gamma 0.9. We have 4 different traffic routes going straight from east to west and west to east, and the other 2 are north to south and south to north. We have 4 different traffic configuration. In the first configuration, we have a similar arrival rate of cars from all the traffic direction, but for the first part of the time period there is vehicles only in the west and east direction, and the second part of the time period there is vehicle on north and south direction only. In the second configuration, we have a equal number of vehicles per second in all the directions. The arrival rate is 0.4 vehicles per second for east to west and north south directions. In the third configuration, we have an unequal arrival rate of vehicles. We have 0.4 vehicles per second arrival rate in east west direction and 0.2 vehicles per second in north and south direction. In the fourth configuration, it is created combining the previous 3 configurations. In the first time period, it has the configuration 1, in the second part it has the configuration 3, and the third part it has the configuration of 3. The first 3 configurations is simulated for 7200 seconds, and the fourth configuration is simulated for 21,600 seconds. To evaluate the performance of different reward functions, we have taken 4 different performance matrices: the average waiting time, the average delay, average queue length, and throughput. Here are the result for configuration 1. From the result we can see that none of the reward function performed well in terms of all the performance matrices. The reward function performed best for the parameter which is used to design the reward function. The reward function designed with delay performed best for the delay, and the reward function designed with queue length performed best for queue length, and same for the waiting time. And the travel time, reward function with travel time performed best for throughput. So here we can conclude that in configuration 1, none of the reward function performed better than all the others. Here is the result for configuration 2. The reward function designed with queue length outperforms the others in terms of all the performance matrices. The configuration is created with a equal number of arrival rates in all the traffic routes. So we can say that if the traffic pressure or arrival rate of vehicles are equal in all the traffic road directions, then the reward function designed with QLength can perform better than the others. Here is the result for configuration 3, which has an unequal arrival rates of vehicles in all the traffic directions. The reward function designed with delay outperforms the other in this configuration. So we can say that if the traffic pressure or arrival rate is unequal in different road direction, then the reward designed with delay perform better than the others. Here is the result for configuration 4. Here, like configuration 1, none of the reward function perform better in terms of all the performance metrics. The reward function designed with travel time performed better for the delay and waiting time. The queue length value and the throughput value for the reward designed with travel time is not far from the best value of queue length and the waiting time, and the difference of the values is not significant. So we can say that in configuration 4, travel time, the reward designed with travel time performed slightly better than the other reward functions. So we can conclude that we have experimented six reward functions for adaptive traffic control system, and we have seen that none of the multi-objective reward function perform better than the single objective reward function, though it is expected to perform well than the single objective reward functions. So one fact can be that the correlation among the parameters which are used in multi-objective reward functions can play a role. They can mislead the reward values, and therefore the multi-objective reward function does not perform as it is expected. So it can be a future research direction why and how the correlation among parameters for multi-objective reward function can be minimized. So thanks for your time.